So the heart of this problem, like some others, is the work-energy theorem. Now the work-energy theorem, the reason that screams out at you, and first of all, you're like, work-energy theorem, what's that? Review your notes, watch that video again, because that's something you really want to get a hold of. It involves, in this case, the key here, what triggers it for me is that when I think of the work-energy theorem, it has two parts, and the second part is the change in kinetic energy. And if any problem out there screams about changes in kinetic energy, it's this one. Because in every one of these cases except one of them, actually with all these cases except one, there is a change in kinetic energy. You see velocity, you have to think kinetic energy first, particularly when you're doing a unit on energy. Even later, when we learn all the topics in physics, velocity, one of the first places I'm thinking, unless it involves a collision, which we'll get in another unit or so, unless it involves a collision, if I see velocity, kinetic energy is my first approach. Kinematics and so forth will be later. But work-energy theorem says that change in kinetic energy is equal to the net work done. Now, in this case, I am thinking that that is what they mean by this, that they want the net work when they say that. So that's a little bit tricky with this one, but I'm going to interpret them to mean net work. And in this case, also, there's really two separate answers, as we'll see in a moment, depending on whether you want to account like magnitude or the negative, how the negative works. I think we're going to include the negative, but we'll see. So that work is done to the change in kinetic energy. So you might be looking at this and saying, all right, well, the one with the biggest change, depending on how you look at it, like this one, for example, this one might have the biggest change. Well, we gotta look at that in a second. But this has a 10 change, and this has a 10, so they're probably about the same. You gotta be careful, because kinetic energy, remember, is 1/2 mv final squared minus 1/2 mv initial squared. And the point is that, first of all, change in final minus initial. The thing you have to be careful of is the squared. When you have squares, it's worth it to do the calculations off to the side just to make sure. So they don't give us the mass, but they're the same car. So let's call all the masses 1 kilogram. That way we don't have to worry about it. So if we assume that the mass of the car is 1 kilogram, then, for example, the change in kinetic energy for A is going to be, let's see, final, so that's going to be 1/2 times 1, okay, times 20 squared minus 1/2 times 10 squared. Let's see, that's 400, that's 200, minus 100, half is 50, so that's 150, if I did that correctly, joules. And that's assuming, once again, you're like, where'd the mass go? Remember, mass is 1 kilogram, so if I multiply by it, it's not going to make a difference anyway. And I would do that for each of them. But you have to be careful. Kinetic energy here, for example, it doesn't care that you're moving the other way. The point is it's just 10. When you square negative 10, you're still going to get a positive. So this one, for example, C, jumping down to it, C is going to involve no change in kinetic energy. It's going to be the same as it was at the beginning. I think it turns out to be 50 minus 50, and there is no change. I'm not saying it doesn't have kinetic energy. I'm saying from beginning to end, it's the same kinetic energy. Getting run over by this car is going to hurt just as much as getting run over by that car. The direction is not important in that case for kinetic energy because it's a scalar. Now this one, I think it's pretty straightforward. There is absolutely no change in kinetic energy there. So for D, we keep the same kinetic energy. Change in kinetic energy is 0. Just by looking at it, hopefully you got that. Same velocity, same kinetic energy. For B, he says, come on, there we go. Now it's end at 0. So for B, I end with 0 joules of kinetic energy minus my initial, which is going to be 50, just like this, right? So I started at 10. And that's going to be negative 50 joules. I lose 50 joules of kinetic energy. I could see you saying, I could see an answer of A, B, and then C and D together, just saying, hey, yeah, I'm not worried about the negative, that the work done is, I could see that answer, I could live with it. I think in this case, let's go with the actual positive and negative bit. So let's say that it's A, and then C and D would be tied with 0, and B would be last because it has negative change in kinetic energy. Remember, you're like, well, wait a second. Well, this is all about work. Where's all this coming from? This is coming from the fact that the net work is equal to the change in kinetic energy, which is probably the biggest thing this is testing. So this I think is the best answer, but I could live with an answer of A and then B and then C and D, kind of assuming that this is work done, the heck with the positive or negative. I could see that, and I wouldn't go and change it all, but make a note of it to yourself. Make a note of it to yourself. Be aware that there are two ways to look at that.